We know everything is made of atoms, so atoms of a given element, say copper, have the same number of protons. So atoms of copper, atomic number 29, will all have 29 protons. That's how you know it's copper. The number of protons with positive charge of an atom is equal to the number of electrons with a negative charge in the atom shells, so atoms are electrically neutral. That third subatomic particle, the neutron, which has no charge, is neutral, is where things get tricky. If you look at a sample of copper really closely, you would find that all of those copper atoms have 29 protons. And all of those atoms had 29 electrons. You would also find that most of the atoms had 34 neutrons. Almost 70% of copper has atoms that look like this with 34 neutrons. But the rest of those atoms, that other about 30% of those atoms, would have 36 neutrons and therefore have a slightly greater mass than these atoms. When you have atoms of the same element with a different number of neutrons and therefore a different mass, those are isotopes of that element. So if there are actually two kinds of atoms of copper that are stable, and this one's a little bit heavier than this one, then which mass is on the periodic table? Well, we take a weighted average of both of those isotopes' masses, and that's what goes on the periodic table. And since the greater percentage, as I mentioned, almost 70% of copper's atoms are this isotope, then I would expect the mass on the periodic table to reflect the mass of this atom or isotope of copper. So let's calculate that mass that goes on the periodic table. We have two stable isotopes of copper in our sample, copper 63. 63 is the mass number for that isotope, and copper 65. 69.15% of our sample is comprised of atoms of copper 63. And they have an atomic mass of 62.929 atomic mass units. Our other isotope, copper 65, have a percent abundance of 30.85%, and those have a mass of 64.927 atomic mass units. Now remember, we said that most of our sample is the lighter in mass isotope, and so our average atomic mass should be closer to this mass than it is to this mass. And if you take a peek right there, you'll find that it is. So we'll see how that number gets calculated right now. To do a weighted average, the first thing we're going to do is take our percentage and change it to a decimal. If 69.15% of the sample is this mass, 62.929 atomic mass units, then we want to multiply that mass by 0.6915. And we get 43.515. That is the contribution to the sample by mass of this isotope. We'll do the same thing over here. We'll take our percentage and change it to a decimal. And that gives it a different name too, from percent abundance to relative abundance. And when we multiply those two, we get 20.030. That is the contribution of mass of that isotope to the sample. And then we'll take those two products and add them together. And their sum is 63.545 atomic mass units. And look, we came really close to the number that's on the periodic table. And that's how average atomic mass is calculated.